Hi everyone, I'm Wonghirundacha, and I'm excited to share with you today audio cross-verification using dual alignment likelihood ratio test. The problem we're interested in is given a short viral audio clip of broadcast news, how can we tell if it's authentic? Since fake news can be easily shared on social media, it's important to tell if an audio clip has been synthetically generated or tampered with. Many previous works have approached this problem by examining the audio clip in isolation and trying to detect artifacts of tampering or deepfake generation. In this work, we adopt a different paradigm and instead approach this problem as a cross-verification task, in which we compare a short viral audio clip against a trusted reference recording. Our requirements are that the system be accurate, robust, meaning it's insensitive to harmless differences such as volume and compression artifacts. It has to be fast to compute, so that verification can be done at scale. Finally, it should be explainable. Because verifying viral clips is a public-facing tool, our predictions must not be black box predictions, but have a justification that can be explained. Here's a block diagram of our approach. At the left is the query input, which is a short viral audio clip that we would like to verify. The system has three main steps: pre-selection, dual alignment, and likelihood ratio test. We will explain these steps in the next few slides. The first step is pre-selection. In this stage, we find the matching audio content in a trusted database of broadcast news recordings. This can be done with any existing audio fingerprinting method. Audio fingerprinting has been solved for most practical purposes, and in our work, we simply assume that the matching reference recording has been found. Note that if a match cannot be found, we can simply declare the viral broadcast news clip to be unverified. This would be the case if the news clip was a completely synthetic deepfake. The key output of the pre-selection step is to find a matching reference recording from a trusted database. Our goal in the next two slides is to compare the query and the trusted reference recording to determine if any tampering has been done. The second step is to compute two different alignments that correspond to two different hypotheses. The first alignment corresponds to the hypothesis that the query is not tampered. In this case, the alignment path will be a diagonal line, and the only unknown is the offset at which the query occurs in the reference. We estimate the alignment path by computing a pairwise cost matrix between the query and the reference using standard MFCC features and a Euclidean distance cost metric, and identifying the diagonal alignment path with the minimum total path cost. The second alignment corresponds to the hypothesis that the query is tampered. In this case, the alignment path will be diagonal, but may contain skips due to insertions, deletions, or replacement tampering operations. To compute the second alignment, we use a previously proposed method called hidden state time warping, which is a variant of dynamic time warping that handles insertions, deletions, and replacements. At the end of the dual alignment step, we have two estimated alignments corresponding to our tampered and non-tampered hypotheses. The third step is to perform a likelihood ratio test between two hypotheses. The idea is to treat each alignment path as a hypothesis and then to determine which hypothesis has a higher likelihood based on the observed features. First, we identify the elements in the two alignment paths that are in agreement. In the figure below, the portion of the alignment paths that are in agreement are highlighted in green. For these matching frames, we model the observed feature differences with their mean and standard deviation. In our case, we use a standard 39-dimensional MFCC representation, so our model for matching frames consists of 39 means and 39 standard deviations. Each of these 39 scalar Gaussian models describes how different a particular MFCC feature is in matching frames. Next, we identify the elements in the two alignment paths that are not in agreement. These elements are shown in the figure below highlighted in red. For these non-matching frames, we construct a model for feature differences, assuming that non-matching features are independent. After this modeling, we have two different sets of models. One set of 39 scalar Gaussian models describing matching frames, and another set of 39 scalar Gaussian models describing non-matching frames. Then we perform a likelihood ratio test on the two hypotheses using the query frames as observations. To make the solution tractable, we assume that the features are independent across time as well as across feature index, resulting in the following formula for computing the likelihood ratio, where the z represents the z-scores computed under each hypothesis. We note that our assumption of independence across time and feature index is clearly untrue, but it is applied equally to both hypotheses, so we do not expect it to systematically favor one hypothesis over another. For our experimental setup, we use the DAPS dataset, which contains high-quality audio recordings of 20 different speakers reading scripts that are 2 to 4 minutes long. We focus on the 100 high-quality, low-noise recordings, compressing the audio to 3 different bit rates. We randomly sample 10 different 10-second segments from each compressed recording and tamper each 10-second segment in 3 different ways to simulate insertion, deletion, and replacement tampering operations, and also include an untampered version as our control. Given our method for generating queries, we have a total of 4,000 queries for a given bit rate and tampering duration. Next are our results. The table below compares the performance of our dual alignment likelihood ratio test approach against an MFCC Euclidean distance baseline. Numbers in the table indicate equal error rate in percentages. So 1.0 corresponds to 1% error. Each row of the table corresponds to a different tampering length. We only show results with a compression bitrate of 256 kilobits per second, since similar trends were seen for other bit rates. There are a few things to notice about these results. First, we can see that the dual alignment likelihood ratio test can detect short tampering operations much better than MFCC Euclidean baseline. Second, we see that the most challenging type of queries are very short replacements. This is because short replacements may not result in a substantially different alignment path, whereas insertion and deletion operations are easier to detect because they result in a global shift in the alignment path. Third, we see that dual alignment likelihood ratio test method has reliable performance for tampering durations down to under a second. For insertion and deletion operations, it has 0.2% equal error rate or less for the quarter-second tampering durations, and has 3.1% equal error rate for half-second replacements. Apart from the equal error rates, the system is also fast in runtime. It took an average of 123 milliseconds to process each query. In summary, we propose dual alignment likelihood ratio test as a method for cross-verifying audio that is accurate, fast, robust, and explainable. The explainability comes from applying a statistical test against 2 interpretable hypotheses corresponding to 2 different alignment paths.